All right, let's jump in. Let's get started here. So, today, we want to spend some time here talking, well, I want to spend some time, I don't know if you do or not, but I do. So, spend some time talking about properties of ionic and covalent compounds. So, just as some review, right? When we talk about covalent compounds also go by another name. Do we remember what that name may be? Molecule, or if we're describing them, we could say that they are, how could we turn molecule into an adjective? Molecular, right? So up at the top, on your outline, where it says properties of ionic and covalent compounds, we could also substitute in molecular for covalence, right? Those basically mean the same thing, okay? Good there. All right. Before we get into that, though, let's talk about the three pictures that are up at the top of your outline. I think most of you are probably familiar with those three pictures, right? Relating the three, or describing the three states of matter, okay? Here's what I want to do. For the first minute, I want you, either with the person next to you or by yourself, to write down what you know properties-wise about solids, liquids, and gases, right? General things about the properties of solid, liquids, and gases. It could be, you know, something simple that you learned back in 3rd grade when you start learning about solids, liquids, and gases. If you know a little bit more, that's great. But take a minute, write down some properties of things that are solids, liquids, and gases. Ready? Go. All right, let's discuss. So, who wants to start? If you start, you have multiple options as far as which way you can go. So who wants to give me something that you guys discussed over the last minute? Eric, go ahead.
For gas, the atoms take shape of the container.
Okay, so for gases, they take the shape of the container that they're in. Sometimes we abbreviate that as no definite shape, right? But that also means, don't erase, I mean, so no definite shape, but also if we put them in a bigger container, right, Eric, what will they do?
Move around.
They'll fill that container, right? So they have no definite shape, but they also have no definite size, right? That they'll fill whatever container they go into. Good.
Is there any gas that doesn't float in water?
That doesn't float in water? No, because the density of gas is so small. We'll talk when we get to density as properties of materials. We'll talk about how that determines where they go in this situation. Yeah, density of gases are so small that it doesn't, you know, all gases will float in water because their density is much lower than liquids. So. All right, so gases, no definite shape, no definite size. They fill the container that they're in. What's next? Liam, go ahead.
They move around density and breathe.
Okay, so whatever makes them up, right? It could be atoms if we're talking about a gaseous what? Let's talk about our terms here, right? It would be atoms if our gas is a what? You said what? Hydrogen. Hydrogen is a specific example of an atoms make up elements. Very good, everybody. Yeah. So it would be atoms if we're talking about an element, right? What else could our gas be made out of? Particles. Let's go something maybe a little more specific than particles. Maybe a word that we've already talked about today. Molecules, right? If we're talking about a compound that is formed by what?
2 elements.
2 elements. What kind of elements?
2 ions.
Non-metal.
Non-metals, because they are joined together with a covalent bond. Can you guys think of any molecular gases?
Methane.
Methane.
Carbon dioxide.
Carbon dioxide, right?
Potassium carbonate.
Potassium carbonate has Ammonium carbonate,
Carbon
maybe. All right. So
monoxide.
carbon monoxide. Okay, we're good there. All right. So let's go to summarize that discussion. Let's go particles, right? Because particles could be atoms, could be molecules, depending on what we're talking about. But Liam, more important than the discussion, what do we know about those particles? How did you describe it? So it was a good description.
They're moving fast and free.
Fast and free, right? Okay. All right. Anything else about gases before we move on to the next part? I think that's about covers it. That's cool. All right. So I guess there's one more thing we could put on there, right? Fast movement. Remember, there's one word that kind of ties all this stuff together, right? What do we say the answer to almost any question in this class could be? Energy, right? So what would we say about the energy of the particles that make up the gas? High energy, right? So particles have high energy. Okay? Good there. All right. Where do you guys want to go next? Liquid. All right. So.
Liquid kind of guy.
All right. So, what about liquids?
No definite shape.
No definite shape. But, Eric, does that mean that they will completely fill the container that they are in?
Nope.
Not necessarily, right? So they have no definite shape, but they have a definite what? Size, or maybe we'll go. What do we call size in 3 dimensions? Volume. Did you say that?
Dominic said it was short
Okay. All right. What else? We can just piggyback off what we did on the gas, right? Okay. So, what else can we say about liquids? Ollie, go ahead. Say again. They move freely, but do they move freely as gases? Right? So, let's say that they move freely, but do they move fast? Not as much as gases, right? So they have freely, but we have to keep that in comparison to our movement of gases, right? The movements, they can move freely, but not necessarily fast. Why not? They're denser. They're closer together, right? That means, as I consider particles, closer together. And that means, what do they do to each other? They kind of get in each other's way, right? There's some interactions there between those particles that make up the liquid, right? I remember when we say particles, we could be maybe talking about atoms, we could be talking about molecules, depending on whatever it is we're doing, right? All right, one last thing to summarize the liquid category. Again, piggyback off of gases, right? Particles, let's go with medium energy, right? They have some ability to move, but there's definitely some restrictions on that movement, right? They have, we'll go, quote unquote, medium energy. Okay? All right, good there? All right. Solids, right? Again, this should be the easiest one now. Let's just, piggyback with what we've done and let's go to solids, right? So solids. Definite shape and definite volume, right? So definite shape, definite volume. Okay? What else? They don't move freely. Do they move at all? Do the particles move at all?
They vibrate. Yes, they
Yeah. There is some motion, but it's more like a shaky, vibrating motion, right? Sure. My pen is kind of acting up today. All right, so particles vibrate. What else?
Particles are very close together.
Very close together, right? And that means they get in each other's way. So much so that they don't have that freedom of movement, right? What else can we say about solids to sort of close it out? Low energy, right? All right, good there. Now, this doesn't necessarily relate to bonding. But what we find out is that the type of bond that holds atoms together plays a role in how these things, or how these substances, these compounds, what kind of properties they have. One of them being what state of matter they're in, but there's some other things that go along with it. Okay? So let's keep these things in mind as we go forward so we can reference them as we're talking about the properties of these compounds. Okay? All right, so here and here. As we just discussed, the physical properties of a substance are affected by how much they interact with one another. And how much they interact with one another is determined by the attractive forces between the particles. And remember, when we're saying particles, we could mean atoms, we could mean molecules. Here we're talking more about molecules, so we're talking about things that are bonded together. Right? That being the case, right? Liam, description of gases, right? How do they move? Fast and free. How much do the particles attract each other in a gas? Not a lot, right? Two reasons. Why? Two reasons why they don't attract each other very much. Well, yes. I'm thinking more like, let's talk about our properties of gases again. They're really far away from each other, and they're moving too fast, right? So the attractive forces in a gas are very low, and that allows each individual particle to move, like we said, fast and free, right? But in a solid, how much attraction is there between the individual particles that make up that solid? Lots of attraction, right? They're very close together. They're very slow, and that allows that attraction to take over, right? And then liquids are somewhere in between, right? The greater the attraction between the molecules, the more energy is required to overcome those attractions. Is something that's a solid always a solid? No. But what do you have to do to make it not a solid? Work, yes, but more generally, like when we heat it up, right? Add energy. Because energy causes those particles to start moving more and more. And if they start moving more and more, now they can move more freely. Now we set into the liquid, right? And they start spreading out more. But the more they attract each other, the harder it is to break them apart. Okay? Good there? And that leads to increased melting point and increased boiling point. Because increased melting point is when something turns from a what to a what? Solid to a liquid. An increased boiling point or boiling point is when something turns from a liquid to a gas, right? The higher these things are, the higher these temperatures are, that indicates a greater attraction between the molecules. Go ahead, Dave. Yeah, everything has a boiling point. So the question was, do solids have a boiling point? Yeah, solid is not a substance, right? It's just a state of that substance, right? Let's use water, because water is the example that we all really know of, right? Water can exist in any of the three states of matter, right? It can be a solid, it can be a liquid, it can be a gas, just depending on how much energy we give those particles. These things right here, right, all the solid stuff in this room, we could turn those particles, give them enough energy that they don't hold on to each other as much anymore and turn it into a liquid. That temperature is just a lot higher for things that we consider to be solids than things that we consider to be liquids or gases, right?
Then about like evaporation,
Yep.
like I don't think you have to heat water to like 100 Celsius to make it into a solid vapor.
Right. So your point is taken, right? That anytime something turns from a liquid to a gas, right? Anytime something turns from a liquid to a gas, it gains energy. When we quote unquote boil something, we just increase the energy of those particles very quickly, right? But you've seen that liquids will turn into gases on their own if they just pick up particles from, or energy from other things around them, right? But, so, example,
But they're not boiling.
they're not boiling. We'll learn that technically boiling and evaporation are the same change. It just happens in a different temperature. Okay, we'll learn that more when we get into properties, right? But, case in point, right? If you have some water on your hand, right? And you like kind of just like gently blow on your hand, you can make that water evaporate. But what does that do to your hand? How does your hand feel then? Well, if it evaporates, not anymore, right? But how does it feel when that water is evaporating? It gets cold. Because where is that water getting the energy from? Your hand, right? So if you have wet hands and you just kind of like do this, you know, to dry them off, yeah, that water will turn into a gas, but where's it getting the energy from? It's getting it from you.
Can a rock evaporate?
What?
Can a rock evaporate?
I mean, in theory. Now, evaporation, turning something into a gas, depends on how tightly those molecules are held together. Things that are solids because the particles are held together very tightly. Can things turn straight from a solid into a gas? Yeah, they can. If you've ever left ice cubes in the freezer for a really, really, really long time,
Oh, yeah.
they like, you go back in there and they're like small. Because those ice particles, those solid liquid particles, have gained enough energy to turn into a gas. Okay? Some substances do that more easily than others, right? If we let this table sit here in this room for hundreds of years, it wouldn't evaporate. That's not what the particles that make up this table do. But water does have the ability to do that. So, again, anything can happen. It depends on what is the nature of that material, but then also how much energy does it have. That's a big question that we have to answer. Sure, go ahead.
When you talk about the ice, is it always trying to get to the highest energy?
Not necessarily. So Charlotte's question was, we talked about the ice and gaining energy and the water gaining energy, and said, is it always trying to gain energy? Technically, what we're trying to do is to make everything have the same energy, right? If you hold an ice cube in your hand, it feels cold because your hand is losing energy. But where is that energy going?
Ice cube.
Into the ice cube. If you held it in your hand long enough, it'll eventually turn into what?
Water.
Water. And eventually, If you held it long enough, it doesn't take a while, but if you held it long enough, it wouldn't feel cold anymore. Because eventually the ice cube in your hand would be the same temperature, right? If you put your hand in water, you get water out of the tap, it feels cold, okay? Because the water that comes out of the tap is a lower temperature than your body. So water flows out of your body into that water. But if you put your hand in water that's 98.6 or somewhere around there, right, your normal body temperature doesn't feel cold, right? If you put your hand in water that's 105 degrees, what does it feel like? It's hot. Why? Because what's happening then? It's transferring heat into you because the water is hotter than you. It's not so much that anything is trying to ultimately lose or gain energy. We want that energy to be nice and even across the board. That's really what's going on. Okay? Usman, you have a question for?
Yeah, but you kind of answered.
Okay.
We have another question.
Good.
When you see like your temperature is 70 degrees in your house, how come like is it cold?
So, good question. Usman says we set the thermostat in our house to, 78 or let's go 70 degrees, right? It would be cold. It doesn't feel cold because of this. Okay? My sweatshirt. This sweatshirt creates a barrier between you and the air in the house, right? If you sat around in your underwear, guess what? It would be cold, right? What happens is that the energy, generally house, right? You're warmer than most things in your house. So energy flows out of you and into those things, like the air. But if you put a sweatshirt on, right, now there's some air trapped between you and the sweatshirt. You'll lose energy to the colder air until the temperature of the air is the same temperature as you. Does that make sense? So by putting this sweatshirt on, I'm trapping this air, and my body warms up that air that's underneath the sweatshirt, and now I'm all good, right? Because now I don't lose any more energy anymore. Does that make sense? Right? But if you jack the heat up, this is too warm, right? Because that air is warmer, and now your body isn't losing as much heat anymore because it doesn't have to heat up the air quite as much. Does that make sense? Yeah. Okay. All right. Good? All right, let's bring it back to bonding. Oh. All right. Up on the board, you are looking at something that says it is a structure of an ionic solid. And here, it's a three-dimensional representation of the structure of that ionic solid. Okay? Those of you in the back, right? Got a picture of what we're looking at here? Okay? Yes? Okay. All right, so I'll leave it right here. All right, so first, ionic solid. What are ionic solids made out of? Ionic bonds, or things held together by ionic bonds. And that means that we got to have what kind of elements? Metals and nonmetals, because ionic bonds form between metals and nonmetals. Okay? Good there. All right. You can see on the picture on the board, right? The little pink circles represent sodium. The big green circles represent chlorine. Here, in our model, even though the size isn't different, the arrangement is still the same. What are you seeing about sodium and chlorine, or at least the pattern? Every other one, right? Because what is positive sodium attracted to? Negative chlorine. And what is negative chlorine attracted to? Positive sodium. Do we see any red or white repeaters in this whole thing? You might not be able to see it totally detailed, but there's not, right? Because this white one that I'm pointing to right here, even though you might not be able to see it in the back, right? It doesn't want to be next to any other whites. Because let's say white is that sodium, positively charged. It doesn't want any other of those positive charges next to it. So it surrounds itself by negatively charged reds. Same thing is true of red. Red doesn't want to be next to any other reds because like charges repel each other. So it surrounds itself with whites. And we get this nice alternating pattern. Red, white, red, white. Now, that's great for sodium chloride, sorry, because what's the ratio to sodium and chlorine in sodium chloride? 1 to 1. It doesn't always work out nice and even like that because sometimes the ratio isn't the same, but we still have a nice repeating pattern of positive, negative, positive, negative, positive, negative, because they're trying to separate themselves from each other. However, that white is surrounded by a bunch of reds. Is that white going anywhere? No. It's attracted to all those reds, but it's also repelled by all the other whites that are in there. So it's locked in that space. What is that representative of in a state of matter? That's a solid, right? Lots of ionic compounds, most ionic compounds, are solids at room temperature because they're nice and locked into each other. Now, David, going back to like your question before, does that mean we could never melt salt? No, we can melt salt. You just got to heat it up really, really high to do it. Because that white in the middle right there, it doesn't want to go anywhere. It's real happy where it is. So if you're going to make it move, you have to give it a lot of energy to make it move.
You
Okay.
guys have a gas salt, right?
You could, yeah, you could turn salt into a gas. It's just got to be really, really hot. Right? Okay. What? Wow. All right, so ionic compounds form a three-dimensional network that we call a crystal, or sometimes we call a crystal lattice. If you look at salt that comes out of the salt shaker, right? Do it today at lunch if you've never done it before. You know what it looks like? It's a bunch of cubes, right? It's a bunch of little cubes because they set themselves up in that nice little pattern, okay? And within that pattern, within that three-dimensional network, right, each ion, right, vocab words, okay, each ion is attracted to multiple ions of the opposite charge. Good there? For starters? Okay. Picture. Let's go here. Let's go here. Ow. Okay. Here is a crystal of salt. Okay? Positive sodium, negative chlorine. Positive sodium, negative chlorine. Positive sodium, negative chlorine. As we move horizontal or vertical. Okay? Back when we first started doing ionic bonding, right? I drew you this picture. Here was sodium with its 1 valence electron. Here was chlorine with its 7 valence electrons. And then this happened, right? Transfer of electrons, sodium's positive, chlorine's negative, cation, anion, and now we end up with this, right? Na attracted to this Cl, right? Like that, but that Cl is holding on to that electron that's sodium cated. Yes? Right? Now, it's real easy here to see this sodium transferred electron to this chlorine, and now they are bonded together ionically. Okay? But where are this sodium and this chlorine in this picture? Well, are those two bonded together? Or what about maybe that sodium is actually bonded to this one? Or maybe it's bonded to that one? Can we tell from this picture? No. And that's the point. It's not, when we have this ionic solid, there isn't, while there is a 1-to-1 ratio of sodium to chlorine, we can't say specifically that this sodium is bonded to this chlorine, or this sodium is bonded to this chlorine, or this sodium is bonded to this chlorine. Why? Because it's not really like that. It's just a bunch of positive ions and negative ions all matched up together in this big structure. Okay? Does that make sense? Within that structure, there is an even number of sodiums and chlorines, but you can't really say this one's attached to that one or vice versa. Okay? So, we say that this is the formula for sodium chloride, the ratio of sodium to chlorine. In reality, we refer to this as a formula unit. A formula unit for an ionic compound describes the ratio of sodium or cation to anion. Okay? It's hard to say that this sodium is attracted to this chlorine, but we know that within that crystal, there is a 1-to-1 ratio. So 1-to-1 is the formula unit for sodium chloride. Okay? Good? Okay with some vocab there? That's going to come up again. So when you see your, I'll get you a objective sheet for this quiz, because it's a little bit longer than the ionic quiz. That is going to show up. So formula unit is the ratio, or describes the ratio of cations to anions within a crystal. A formula unit describes the ratio of cations to anions in the crystal. Okay? Good? Okay with that so far? All right. Turning back to our slides. Okay. We talked about at the beginning the attractive forces that hold things together. How strong are the attractive forces in an ionic solid? Very strong. That's why most of them are solids. We refer to those attractive forces as interionic forces. Right? That makes sense? Right? Inter means between. Right? Ionic means ions. Interionic forces. Okay? Interionic forces come from the attraction of oppositely charged ions. Specifically, what do we call oppositely charged ions? Or what are the two oppositely charged ions? Negative and positive. What do we give them names? The negative one is the anion, and the positive one is the cation, right? So interionic forces are the attraction of cations to anions. There is a greater attraction between ions of greater charge. All right, ready for pop quiz? Okay, you've already written down, or if you haven't written down yet, you know the formula units for sodium chloride. Okay? Either by yourself or with the person next to you, figure out the formula unit for the compound barium oxide. What is the formula unit for barium oxide? Go. for barium oxide is BaO. Okay? However, I guess we go here. Ratio of barium to oxide in the formula unit is 1 to 1. What's the ratio of sodium and to chlorine and sodium chloride? 1 to 1. But there's a difference though, right? What ionic charge does barium have? +2. What ionic charge does oxygen have? -2. The interionic forces in barium oxide are stronger than the interionic forces in sodium chloride. Would the crystal look any different than this one? It doesn't look any different, right? But it would be stronger well, they might be tighter together, yes. But I was thinking more on the opposite end, right? What would that change about barium oxide versus sodium chloride? It'll be stronger. What will that change properties-wise? Has a higher melting point because it's harder to separate them. Yes, no, maybe? Okay. So, these are, interionic forces are the strongest forces between particles that we know about. And that's why ionic compounds, generally speaking, have the highest melting points and the highest boiling points of any kind of compounds. And so, right, I think this will be our last one for today. That means that they have high melting points and high boiling points, right? Hold on a second. We still have 5 minutes left. Just because the last slide doesn't mean you can start putting stuff away. Let me finish this. All right, so high melting points and high boiling points. That means that they are solids at room temperature for the most part, right? All right. You don't have to worry too much about the why on the next couple, all right? But know that these are general properties of ionic compounds. Many of them are soluble in water. That means when you mix them with water, they dissolve. Okay? Also, if we turn them into liquids, they become very good conductors. Not so good at conductors when they're solids. Because in order for conduction to happen, right, conduction is current, what has to be true? What is our definition of current? Electron. The rate at which electrons flow. Are there any electrons flowing in here? There's nothing moving in here because everything's real strongly attracted. But if you get them separated from one another, like in a liquid, now they have the ability to flow from one to the next to the next. Okay? Good there? All right, we'll pick up molecular compounds tomorrow. Good job today, everybody. Good questions, good answers, good drawings.